Hello, Pixios. Sorry I couldn't stream earlier, but yeah, I'm all caught up. Currently going through the big O notation. So keep up, enjoy the music.
Very cool algorithm. Very powerful algorithm. Here's a slightly different example worth going over. So first, notice that there is an outer loop with a counter I that does n work. Then notice that there are two inner loops, one that does 3n work and another one that does 2n work. So the rule we use to determine the complexity of this algorithm is to multiply loops on different levels and add those that are the same, generally speaking. So using the rule above, we can see that it takes n work to do the outer.
Let's quickly go over the rule of love. Look, street. How do you say love in a Bobby accent? Huh? Quelle love? J'ai dit portao, yes please. Magali, love. Prophet.
Loop. So using the rule above, we can see that it takes n work to do the outer loop, multiplied by 3n plus 2n for both inner loops, which gives us 5n squared, which is big O of n squared. Alright, so this next one looks very similar, but it's actually quite different. So on the outer loop with I, we have I going from 0 to 3n. So there's 3n work done on the outside. But we have to multiply that by what's going on the inside. So on the inside, j goes from 10 to 50. So that does 40 loops exactly, every loop. So that's a constant 40 amount of work. Plus, however, the second loop. So j is less than n cubed, but j equals j plus 2, so it's accelerated a little. So we're going to finish that loop a little faster. So we're going to get on the inside, 40 plus n cubed divided by 2. But we have to multiply that by 3n. So if we wrap that in a big O, so big O of f of n, is going to give us big O of n to the fourth, because n to the fourth is the dominant term in our function f of n. There's some other classic examples of big O. So if we have to find all the subsets of a set, that takes an exponential amount of time, because there are 2 to the n subsets. Finding all permutations of a string takes big O of n factorial. Another classic one is merge sort. So if we have n times log n for your merge sort. And if we have to iterate over all the cells of an array of size n by m, we have big O of nm time. All right, let's talk about arrays.
In this lesson, we will see how to deduce and calculate running time of an algorithm and analyze the time complexity of it. The actual time taken by an algorithm, or what we also call the running time of the algorithm, may depend upon a number of factors, and let us see what those factors are. So we will say that running time depends upon factors like whether your machine is a single processor machine or a multiple processor machine, and maybe also upon which generation of processor you have. Running time also depends upon what is the read or write speed onto the memory of your machine. So we'll say that read or write speed to memory or disk, because your program may have or will surely have a lot of input output operations. Running time also depends upon whether your machine is a 32-bit architecture or a 64-bit architecture, and it may also depend upon a couple of other factors or aspects relating to the configuration of your machine on which you're running the program. And last but not least, complexity analysis for various inputs, or how the time taken by the program, all these factors. All we bother about is that how our program behaves, rate of growth of time taken with respect to the input. Now, how do we calculate an expression that gives us the rate of growth of time of an algorithm with respect to the input? To do so, we first define a model machine where we will execute our program. So let's say we define a hypothetical In this lesson, we will see how to deduce and calculate running time of an algorithm and analyze the time complexity of it. The actual time taken by an algorithm, or what we also call the running time of the algorithm, may depend upon a number of factors. And let us see what those factors are. So we will say that running time depends upon factors like whether your machine is a single processor machine or a multiple processor machine, and maybe also upon which generation of processor you have. Running time also depends upon what is the read or write speed onto the memory of your machine. So we'll say that read or write speed to memory or disk, because your program may have or will surely have a lot of input output operation. We talk about time we're interested in algorithm with respect. It is a single processor machine. architecture of the machine, subtraction, multiplication, division, and return, and let's say all other costs are negligible and we do not account for it. Now this is a hypothetical model machine that I have defined, and you can define costs are negligible and we do not account for it. Now this is a hypothetical model machine that I have defined, and you can define a model machine of your own choice where you can say that, hey, the machine takes this much amount of time for this operation, but because eventually we are interested in calculating a function that gives us the rate of growth of very simple examples and try to, let's say we want to write a program to find the sum of two numbers a and b. So I will write a function here that will take two integers a and b and simply return a plus b, and I'm only writing a pseudocode here. Now if I want to run this particular function using the model machine, then let's say if the time taken is t, and let's say this is t sum, then 1 unit of time for the arithmetic operation addition and 1 unit of time for the return statement. So the total time would be equal to 2 units. So in this case, irrespective of the input to the program, the time taken is exactly 2 units. Or we can also say that the time taken is always constant. That is, say this is function using the model machine, then let's say if the time taken is t, and let's say this is t sum, then 1 unit of time for the arithmetic operation addition and 1 unit of time for the return statement. So the total time would be equal to 2 units. So in this case, irrespective of the input to the program, the time taken is exactly 2 units. Or we can also say that the time taken is always constant. So this particular program is a constant time algorithm. Now let's pick up another example.
A bar, two strangers.
Let's say we want to write a program.
A bar, two strangers, a look. Music changes everything. That's why SEAT proudly supports Primavera Sound. Click here to transform your playlists into new sounds and change how you experience your daily moments. See the world through your ears. SEAT.
Barbershop singers from Gloucestershire, with a joint mortgage and a credit card for over a year, has an Experian credit score of 862, and to his friends he goes by the name of Hugh.
At Experian, we know everyone's one of a kind. That's why we use your credit history to help find deals that are right for you and only you. Hugh. Visit Experian.co.uk. Experian Limited is a credit broker, not a lender. T's and C's apply.
That gives me the sum of all the elements in a list. So I would write a function sum of list that will take a one-dimensional array a as input, and let's say it also takes as argument to the function the size of the array. So the size of the array is n. So in this case the program goes like, so we start with a variable total and the array is n, and let's sum of list that will take a one-dimensional array a as input, and let's say it also takes as argument to the function the size of the array. So the size of the array is n. So in this case the program goes like, so we start with a variable total and we initialize it to 0, and then we run a loop and keep on adding the elements of the array into this particular variable, and finally return it after we come out of the loop. And before we calculate the time taken, let's do something here. I will label these statements with line numbers 1, 2, 3 and 4. Now line 1 has one assignment, so the cost will be 1 unit, and this particular statement will be executed exactly once. Line 2 has one comparison, which is often there in a loop, and since I've written a pseudocode here only, so let's assume that we have one comparison and one incrementation, and both have cost 1 unit each, and the total cost to execute line 2 is 2 units. And this will execute n plus 1 times, one extra time for the false condition when the program actually exits the loop. And this also has a cost of 2 units, one for the addition and one for assignment here. So this executes n times, and the last line is a simple return which executes once and has a cost of 1. So the total cost, let's say, is t sum of list is equal to 1 plus 2 into n plus 1 plus 2 into n plus 1, and this eventually evaluates to 4n plus 4. Now if this sounds a little messy to mark these absolute terms here in cost, we can also write some constants here, like the cost of executing line 1 is say C1 and the cost of executing line 2 can be called C2, and we can go on like this. And then also we can try to calculate the total cost. So in that case we will arrive at some expression like time taken is a function of n, Tn, which is equal to some constant, let's say C times n plus another constant C dash, where C is equal to C2 plus C3 and C dash is equal to C1 plus C2 plus C4. But these constants are not important because we are interested in the rate of growth of the time taken, and in this case clearly the time taken grows as a linear function simply because it's proportional to n. So for the first example that we had picked, we had the time taken to sum of two elements equal to some constant, let's say this constant was k. The second example was where we wanted to have the sum of elements in list, and in this case our time taken was a linear function of n, something like c into n plus c dash, where c and c dash are some constants. If we want to print the static function like this, and if we try to plot these three functions on this graph, then we get something like this. In fact, x-axis here is and should be input size, so we can call it, let's say, n. Clearly, for higher values of n, the rate of growth of, we often classify functions in all the function n is the set of all the functions of this particular form. All the functions, and this is the same big O notation that function and asymptotic and omega. Big O is actually called an asymptotic notation. So this big O that we often write is called an asymptotic notation. And we also have other asymptotic notations like theta and omega, and we'll learn about all of them in the next lesson. So thanks for watching. In this lesson, we will learn about the concept of
Lesson 6. Big O, Big Omega, and Big Theta notation. When we speak of an algorithm's efficiency, we want to determine its scalability. That is, we want an algorithm Big Omega and Big Theta notation. When we speak of an algorithm Big Omega and Big Theta notation. When we speak of an algorithm's efficiency, we want to determine its scalability. That is, we want to know that when the algorithm is applied to a large dataset, that it will finish relatively quickly. We can also talk about how much memory an algorithm requires, but for now we will focus on speed. We measure an algorithm's speed in terms of the growth in the number of operations we measure an algorithm requires, but for now we will focus on. We can also talk about how much memory an algorithm requires, but for now we will focus on speed. We measure an algorithm's speed in terms of the growth in the number of operations relative to the input size. For the linear and binary search algorithms, for example, the input size is the number of elements that we are searching. Typically, we will use the letter n to represent an unknown input size, and we will talk about the growth in terms of n. To formalize our ideas of growth, there are three types of bounds that we will address here: Big O, Big Omega, and Big Theta. The definitions that we will use come from mathematics and are used to relate the growth in one function relative to another simpler one. Here we have the graphs of two real functions f of x and g of x, given by the gray and dashed arrows, which we use to indicate that the functions continue indefinitely. The function f of x is more complex, and we want to measure its growth in terms of the simpler function g of x. More specifically, we want to find a constant such that when we multiply it by the function g of x, it will bound the function f of x above from some point onward. Assuming that the graph of f of x does not intersect the graph of c times g of x after the point x0, we know that the graph of f of x remains in this white region for all x to the right of x0. In this case, we say that f of x is in big O of g of x. Formally, we say that f of x is in big O of g of x if there exist positive constants c and x0, such that f of x is less than or equal to c times g of x for all x greater than x0. On the other hand, we could bound the function f of x from below, like this. If such a constant exists such that c times g of x bounds f of x below from some point onward, then we say that f of x is in big omega of g of x. Formally, f of x is in big omega of g of x if there exist positive constants c and x0 such that f of x is greater than or equal to c times g of x for all x greater than or equal to x0. If there are constants such that g of x bounds the function f of x both from below and above, then we say that f of x is in big theta of g of x. Of course, the constants in this case are different, so we have labeled them shown with like the size of function times g of x for all x greater than or equal to x. The input size is generally a positive integer, like the size of an array for a sorting algorithm. In this case, we can think of our f and g as functions on the positive integers. In mathematics, x is used to signify a real variable, while n is used to signify an integer variable. Like Hungarian notation in programming, this notation allows us to see more immediately what is going on, so we will use it. Using this notation, here we see the graphs of two example functions f of n and g of n, given by the solid gray and hollow black dots respectively. Notice that the graphs are made up of single dots instead of curves. This is because the functions are defined on integer values. Just as we had for the real functions, we can have constants such that when we multiply g of n by them, we bound f of n from some point onward, and the definitions are analogous. Here we have a constant multiple of g of n is 2 of n from 3 on, so we can set n0 to 3, and we have f of n in the positive integer. We say that c times g of n, big O of g of n, if there exists a positive real number c, if there exists a theta c less. We will give concrete examples of how they apply to specific algorithms so that these ideas become clearer.
I have a new update. I contacted the engineering department at NASA and found out the new rover is using the same memory platform used on Curiosity. And the Curiosity rover was equipped with two computers, but only one was active at a time, and it had the following specs: 2 gigabytes of flash memory, 256 megabytes of random access memory, and 256 kilobytes of read-only memory, which held core system routines. We want to be able to store our entire program in RAM. However, because we have to share this space with other programs, we are allocated 5% of RAM, which is the maximum we can use. And this is about 12.8 megabytes total. I bring this up because I want to introduce the idea of time-space trade-off, or space-time trade-off, a commonly used term in computer science. I was looking at a program done by IV46, and they had a million prime array, so that their algorithm could step along on primes only as far as possible when doing a trial division primality test. And it begs the question, why not just store all the primes we need up to some limit in an array instead of calculating them on the fly? We mentioned in a previous video that this would be optimal for a trial division algorithm. Although you may see his algorithm does not use many steps, it began to run very slowly and eventually crashed before hitting the step limit. so it wasn't able to quickly solve the problem for the sizes I defined earlier. And in this case, they were trading off time in the form of repeated divisibility tests at the expense of space, which is memory to hold the array. Now, why didn't this work? Well, let's do a rough calculation using what we've learned to find out if this method is possible using our memory limit. Remember, we must be able to deal with numbers up to just over 9 quadrillion. And our trial division algorithms only need to check for factors up to the square root of a number, and if it hits that point with no factors found, it can say 100% whether or not the number is prime. Now, how many primes up to the square root of this limit, where the square root of 9 quadrillion is 94.9 million? How many primes under 95 million? Well, luckily, we have learned a mathematical solution to approximate this answer using the prime number theorem. So how many primes are there under x? Well, it's x divided by the natural logarithm of x. And if x is just over 94.9 million, we find the number of primes is approximately 5.1 million. Now, because we are storing these primes, we need to know the size of the largest prime, or in this case, the 5.1 millionth prime approximately, which we know will be some number less than 94.9 million. Now, I double-checked the table, and the actual value of this prime, the largest prime we would need to store under the square root of our limit, is 89,078,611. Now, how much memory does this single large prime number require? Well, to find out, let's convert the number into binary notation, which is how the computer will store the number using tiny switches in memory. We learned about this in the computer memory video. In bits, the largest prime looks like this, which is 24 bits, or 3 bytes needed to store this single number. So let's say we want to store each number in memory, and since we know the largest number requires 24 bits, we can just imagine a long list of 24-bit blocks storing each prime number. So how many bits are needed for this entire list? Well, the memory needed is the number of values, or the number of primes.
A bar, 2 strangers, a look. Music changes everything. That's why SEAT proudly supports Primavera Sound. Click here to transform your playlists into new sounds and change how you experience your daily moments. See the world through your ears. SEAT.
Times the space per value.
Sometimes you don't quite
So we have around 5.1 million values.
country or classic R&B, EDM or emo. Sometimes you just got to skip through until you find just what you're looking for. Right now, you're limited to 6 skips per hour. But on Premium, you get all the skips you want. Want to try it out for 3 months? Tap the banner to learn more.
Times 24 bits per value, which is just over 124 million bits, or if we convert it into bytes, it's about 14.7 million bytes. Call this almost 15 megabytes. So it is not possible to store even a list of these numbers in memory using our limit. And this is just a toy example. It's actually an underestimation of what you'd really need. For example, an array needs space for a pointer to each item, and each pointer on a 32-bit machine is 4 bytes. So the actual amount of memory needed is much more than 15 megabytes. That being said, we know that storing all primes up to the square root of our relatively small limit is not even possible with our memory limit. We can't do it this way. Okay, well, modern day cryptographic systems use 512-bit or even larger numbers, making search and enumeration impossible. Now, for example, if someone asks you to make a list of all prime numbers up to primes which are 200 digits in length, you shouldn't even consider it, because the hard drive needed to store all these primes would be heavier than the mass of the observable universe. I'll leave the calculations for you to try next time. Store all these primes would be heavier than the mass of the observable universe. I'll leave the calculations for you to try next time you're at a restaurant with crayons and paper all over the table. But remember, there are around 10 to the 80 atoms in the observable universe. That's an 80-digit number. Realize now there's a fundamental limit for how much space or memory we have access to. Never mind how much time it would take. But there is always this push and pull between using space or time to solve our problems. So to solve this problem of testing for primality, quickly, using a small amount of space and a small amount of time,
Probably the
then I can tell what the algorithm is returning, and then I can try to abstract what's happening, okay? So the point of example was for you to see that the best way to solve something like this you could figure out just by looking at it, but when things are a little more complex, this is the way to do it. You play with whatever the values in the variables are, how things are changing, okay? And then you see what is returned. All right? Questions there? This is, I mean, you should know this already, okay? So another example. Can you tell me what this is doing? Sorry, pass by value? Sorry? Yeah, okay. Everybody here or just a few? Just a few. Okay, so there's a difference on, there are two different ways that we can pass arguments to programs. Java always uses pass by value. C++ you can use pass by value or pass by reference. Okay, when you pass an argument by reference, you're passing a pointer to the place in memory. So I could be changing what is in here, being passed in as a parameter. So I can change what is in the array after this stops executing. If I am passing by value, then I'm passing actually a copy of the array. And even if I change something in the array within this particular function, when I come out of here, the original array that was used to call the function won't be changed. Do you understand this? So you'll need this more on C++. In here, we will always be using pass by value in this module, okay? But I'm mentioning this because if you were passing by reference, you are changing the array. If you're passing by value, you can put whatever you like on the array. It won't change the array outside this function, okay? So one of the things is, if it was pass by reference, I'm setting, so I did this on purpose to be able to talk about pass by reference versus pass by value. So if I am passing by reference, I can change all the elements in the array to be 0. What else is this doing?
Counts how many,
Oh.
yeah, how many items for the I was changed. The bar actually, the I collects, no bar collects all the.
Yes, perfect. So the person behind you just said, it counts how many zeros we have in the array. So that's what it's returning. It's how many zeros were there in the array to start with. So if the value in the array at that particular point in time was 0, it adds 1 to bar. So bar is counting how many zeros were there in the array to start with. Okay. So I just wanted to use this example to show pass by reference versus pass by value. Time for a break, 5 minutes. We'll continue soon. I'm resuming lecture capture. I stopped it. Yeah, I stopped it during the break, so we didn't need to waste time removing the noise afterwards. So here are some known algorithm examples. So by known, I mean known to you. So are these and one search. Why were these types of sorts? Now, and one search, binary search. Now, why were these the examples that you saw last year? Okay, you should always wonder why you were taught something. Why are people spending time telling you about something? Okay, so why should you care? And did you notice something? I mean, 4 of them are solving the same problem, right? So 4 of them are sorting algorithms, and one of them was a search algorithm. So why? So Schwag's answer was it's because these are popular algorithms, so it makes sense to explore. Yes, but why so many sorting algorithms? And why sort and search? It's easier to search once you sort. Yes. And why do we sort, or why should we care about sorting or searching? You could do them all in arrays, so that was a good introduction to you to this kind of concepts. Yes, you didn't need to know of more complex data structures in order to learn about algorithms and explore different kinds of approaches to solving a problem. So yeah, that's true. And the other thing is that actually sorting and searching is a part of most problems that we'll ever have to solve in computing. There is a lot of sorting, a lot of searching that needs to take place, and it's easier to search if you have sorted. Easier as in less expensive, okay? So that's the reason why those were the examples that you saw last year. So searching is a very common problem to have to do with computer systems, and in order to search, it's easier, as in faster, cheaper to search if things are sorted than if they are not. Okay? Clear? Cool. All right, computational complexity. Again, you saw a bit of this already last year in Introduction to Algorithms. We will just do a very brief refresher, and we're moving on from there because we will need these concepts here. So what are we talking about? So just do a very brief refresher, and we're moving on from there because we will need these concepts here. So what are we talking about? So when we're talking about complexity in this context, we are takes memory that to execute that particular algorithm consumes. Okay, so how much memory is consumed in order to execute that particular algorithm. Again, why do we care? Why do we care? We care because memory at times is expensive, so we might need to save memory, and we're willing to compromise in time in order to do something in a way that uses up less memory, and otherwise we don't necessarily need to care about memory. When we don't have to care about memory, then runtime is what we go for. It's what is the fastest, what will give us the fastest result. There are different considerations in terms of best, worst, and average case. So some algorithms are faster in average. So the average case, for example, in the average case, the time complexity will be a given value, whereas others have a better best case. Okay? But you have to think, well, how many times will I have that best case? How many times will I have the worst case? So some have a better worst case, some have the same best, worst, and average case very closely aligned. So those are considerations to be taken when making decisions. And we represent complexity by how it grows in terms of given how long it will take. Okay, so that's how. So for the average case, we use the big O notation, which you've seen already. This is the mathematical case. So for the average case, we use the big O notation, which you've seen already. This is the mathematical definition of the big O notation. You don't need to know it for this model. I'm showing it so you understand where this is coming from. But what it's giving us is an upper bound to how the time or space consumption bound we have to take when we're making these decisions of which algorithms or data structures to use. So saying that an algorithm is order of some function of n being the size of the input, means that it grows, so its complexity, if this is for space complexity, it means that the memory consumption will grow no faster than that particular function on the size of the input, okay? We often omit the word in, as you saw, I just said, saying that an algorithm is order of some function of n, so I did notation. Is that if we scale it by a constant, we remain in the same level. So if something took the same, so if it was given an array of size n, this will take order n to execute. If I say it will take order 2n or 3n or 100n, it doesn't make a difference. It's all order n. Okay, so we ignore the constants. When we have addition of one function of n with another function of n, the result is that the greater term dominates. So in this case, we're assuming here that gn is bigger than fn, and this is actually represented here by saying that if fn is in order of gn. So if gn was n squared and fn is n squared is bigger than n, so the bigger term dominates. Okay, that's what this means. It's the greater term dominates. When we have multiplication, we actually multiply the functions themselves. So if we have something that's order fn times something that's order gn, the result is something that is in order of fn times gn. We will see examples in the next slides. And logarithms, we ignore the base. So we say that order of log n in base a is the same thing as order of log n in base b. Okay, so we just ignore the bases. We omit the bases. It's just order log n. Now, here are some examples. Let's do this together. Here are some examples. Order log n. Now, here are some examples. Let's do this together. Here are some examples. Some examples. Let's do this together. Here are some examples. Okay. Multiplication, addition. Do you know when this comes to play? So do you know, for example, if we have sequential phases in an algorithm, so one structure followed by another, what you do is you add them up. Okay, so that's why we saw addition and multiplication, because addition is for sequential phases. Multiplication is if we have, for example, one nested loop. So one loop nested inside another loop, you multiply the times that each one of them runs, so each of the loops run, to get the overall running time. Okay, so that's why we care about addition and multiplication. So in this case, if we have, so orders of sequential algorithms are added. So if we have a phase that is order n squared followed by a phase that is order log n log n, sorry, the result is, because they are sequential, so one following the other, we add them up. So then it's order of n squared plus order of n log n gives us order n squared. How did I get to order n squared from this sum? N squared is bigger. The larger term dominates. That's good. So that was rule number 2 in the previous slide there. The greater term dominates. So that's how we got to that n squared there. Now if I have this one, 3n log n plus 100n, so one phase being 3n log n, followed by another phase that is 100n, followed by another phase that is 10 log n, followed by another phase that is 23. What does this mean? What is the big O for the whole thing, for the whole shebang? So how do we get there? That was correct. So how do we get there? First, we can ignore the constants. Remember, that was rule number 1. So we can ignore the constants. So this goes away. Actually, if I had something that just said, I need 23 to run this particular algorithm, what does that mean? So O1, exactly. It's a constant, so it's O1. Fine. I'm just trying to see where you are. And so forgive me if I'm sounding too basic then, because I'm trying to see where you are so far. Okay, so we ignore all the constants. So we have n log n plus log n. Which one is the largest? It's n log n, so that greater term dominates. Fine. Another example now is about multiplication. So I said if we have nested loops, thank you for focusing. If we have nested loops, we multiply, and so that's what's going on here. If we have an outer loop that is executed order n squared times, and an inner loop that is order n times, with its contents being order 1, so it is just an assignment, if, then else, whatever, nothing, no loops inside, then what do? We multiply the 2, we multiply n squared with the n, so order n squared times order n gives us order n cubed, so that was the third rule, that we multiply things, and this is applicable when we have nested loops. In that case, what would be the ON of this particular program, this particular algorithm? N squared log n, that is correct. So we ignore the constants, and then here we have a multiplication that becomes n squared log n plus log n, and then the biggest is this one. It dominates, so that's what it is. Okay, good. Thank you. You make me feel comfortable and happy. Let's go back to the slides. Okay. So these are common types of complexities that we find, and you've seen them before. We say that, can't move farther away, we say that constant, logarithmic, and linear are good performances, so that's good enough. These are good complexities to have. Quadratic and cubic can be acceptable, sometimes polynomial, but it's right. Yes, so I'll go when we say, right, so that's not when we say, so yes, so I first check for if it is telling me is that if I have an array of size 20, 100 of them together, find the, is it after here, find the middle place, and we decide, so we're searching through something that has already been sorted, and we decide, is it here, is it before here, or is it after here, and then we only need to look at half the input, and then again we have the input, and we have the input, and we have the input, so we're not looking through all of the entries, we're having every time, so that's a log n complexity, and so this is what it would look like. So compared to sequential search, in binary search, if you have 120 elements, the average cases that you would run, so going squared, again, major diff, something to be used in thousands of, it's fabulous. Why we should care, and that's why for hundreds and have looked through it for hundreds of care, and that's why we look at this. This is already, so this is already going concepts here. Okay. So this is already going into higher numbers to do this. How do we find order of complexity using sequential search? Right, so this was again just pointing out that bigger numbers really make a big difference. All right, how do we find order of complexity of something? So we can do this one again together. Do you remember how to do this? Will you tell me how you would do this?
Let me put my calm voice on and tell you that
it shows there before it shows here.
You can get 60 days free access to Headspace with pay-as-you-go rewards on 3. Hashtag phones are good.
Search 3 pay-as-you-go rewards.
More action, more intrigue, more competition. Get more from your PS4 and join your friends online with PlayStation Plus. Every month enjoy new PS4 games at no extra cost. Get exclusive.
Okay, so how would we do this? How would we, you know the complexity of this one, order of complexity of this one. How would you go about finding the time complexity for this?
Power up your play. Search PlayStation Plus.
Yeah, how many times does the loop execute? That's what we would be looking for. So here we have one loop, and inside it, so these are constant, right? These are just assignments. So these are constant. Another assignment constant. If, it's just checking a condition, and then we have an assignment, whoops, this should have been an arrow. And if, so else if another condition and another assignment else, just return something, and return something. So everything else is just constant, okay? Now we have one loop. So in order to find the complexity, the time complexity here, what we need to look at is how many times we will execute this loop, okay? So for that, we have to see how low and high are changing. And if we look at this here, we can see, so high will be changing and low will be changing according to this mid, and mid is being calculated by looking at the half. So every time we execute this loop, either I lose the top half of what I'm looking at, or I lose the bottom half of what I was looking at. So I'm always dividing the input size, so the size of the array that I'm considering, I'm always dividing it in half. Okay, so I'm dividing half. Then half again, then half again, then half again. So we know that this is order log n. Okay? Questions? All right. What if I was looking at this one? Question? Questions? All right. What if I was looking at this one? How long does it take? So what do we need to look at here? The loops. Again, we have two loops. One loop, another loop. Okay? How many times are we executing the outer loop? As in order of complexity, not exact. So we have to see. C starts as 1. How does C change? If it's less than the length of the array, blah, 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 plus 1. So it will be plus 1, plus 1, plus 1 until we get to the length of the array. So how many times does this outer loop execute? Order n. Cool. So this outer one is order n. Okay. It's order n. How about this inner loop here? Order n as well. Sorry, the inner loop doesn't go to there, it goes to here. And it is order n as well. So C1 starts with 1. And again, it is plus 1, plus 1, plus 1 until it gets to the length of the array. So this one is order n as well. So what is the time complexity for this particular algorithm? N squared. Thank you very much. And on the other one, we said log n and we didn't write it. Now it's written. Okay, cool. I'm happy. Are you happy? Yes. Did I lose anyone? Okay. All right. This one that we saw just before today, how long does it take? N. I heard N. That's right. That we saw just before today, how long does it take? N. I heard N. That is correct. I starts at 1, incremented by 1 until we get to the length of the array, so order N. This one we also saw earlier today. I heard N. That is correct. I starts at 1, incremented by 1 until we get to the length of the array. So order N. This one we also saw earlier today. Time complexity. N. Space complexity. I was just trying to see if you had seen this, if you knew how to deal with it. So I heard a constant here, that is correct. Fine. Have you seen anything that was not constant yet? Cool. Very good. All right. So here you go, some examples of known algorithms, as in this case, known algorithms is not necessarily algorithms that you know, but it's algorithms that are out there a lot in the literature and are mentioned or used often. So some of them are quite fast, some of them are so well-known collections. If okay, so and test it in a polynomial but problems. Each one. What did you say? Somebody else said something else? Huh? Because it's humble. Yes, because.
Today we're going to see
Hope you enjoy that. Have a great break. And I'll be back very soon.